Hi, it's my pleasure to present our work on Computable Rényi mutual informations, area laws and correlations, which has appeared in Quantum this year. It is joint work with Álvaro Alhambra, Georgios, Styliaris and Ignacio Cirac, and it has been done at the Max Planck Institute for Quantum Optics. The motivation for our work is to look at the mutual information. This is given by the expression of differences of entropies that you can see here, with entropies of the full state and the reduced density matrices on two sides of a bipartite system, and it is a measure of classical and quantum correlations. Computing this measure, however, requires usually to diagonalize the density matrices and is therefore infeasible for a multipartite quantum system in many body states. Therefore, the motivation of our work is to find a different measure of correlations with a similar interpretation, but one that is computable for matrix product operators, which are a standard technique in numerical many-body physics, but also interesting in quantum information. It's also interesting to say that our work gives an application of Rényi divergences in many-body physics, which has previously mostly appeared in quantum information. The way we define this quantity is not using the previous definition using entropies, but using the definition of the mutual information using a relative entropy. The mutual information is the relative entropy between the state rho AB and the product of reduced density matrices on both sides. We generalize this by replacing the relative entropy by the Rényi divergences, of which there are several versions. Two of them, which we are mostly interested in, are the geometric Rényi divergence, which appears in our proofs and is given by the expression you can see here. It has been recently introduced, and also the maximal and measured Rényi divergences, which help us to achieve our goal to give a relational expression for the quantity we introduce. The maximal Rényi divergence appears as a limit of Rényi divergences, but it also has the following compact expression. It's a logarithm of the infimum of real values lambda, such that the operator inequality rho smaller equal to lambda sigma holds. Rewriting this, as you can see in the second line, helps us to write this as a set of values such that the smallest eigenvalue of the operator lambda sigma minus rho is non-negative. We can do this by using the DMRG algorithm to find the smallest eigenvalue, or the ground state, of the operator lambda sigma minus rho. This can be efficiently done as long as the operators sigma and rho are given as matrix product operators. Also, we want to check whether the properties of this new measure of correlations coincide with those that we want. One of the properties that does hold is its non-negativity, as a measure of correlations should not give negative correlations, which doesn't make much sense. Also, another thing that is consistent with the measure of correlation is that it should be non-increasing on the local operations, which basically defines what a measure of correlation does. Both of these two properties are opposed to what has been achieved with a different definition that has been used previously, using only Rényi entropies and the other definitions that I mentioned in the beginning. As a third point, we also achieved to prove thermal area laws in several cases. These should hold as one thinks of thermal states having only correlations at the boundaries where the interactions take place. So correlations should scale with the boundaries. We get the proof of these statements by relating our quantity to a product of a thermal state of a non-interacting Hamiltonian and the inverse of a thermal state of an interacting Hamiltonian, and bounding the norm of this operator. This can be done either by a lemma of Araki or also by using techniques of imaginary time-evolved interaction Hamiltonians. A fourth point is proving area laws for projected entangled pair operators. These represent states with small correlations a priori, and so we expect them to have an area law. We can prove this at least assuming that the projected entangled pair operators has a local purification. Finally, and obviously consistent with an interpretation of being a measure of correlations, is that our quantity bounds correlation functions, just as the von Neumann mutual information does. This statement in the proof relies on a Pinsker inequality known from information theory. Thank you for your attention.